A ball will continue to roll on a frictionless corridor forever and ever, also called as Newton's first law. But this video is to discuss the uniformly accelerated motion such that the velocity is changing at a constant rate. What if a droplet wants to find out its speed at a particular moment? Just like the woman in my right, she questions about her speed at right that moment, called as her instantaneous speed or instantaneous velocity as the case may be. Well, that sends Phi into a real trouble. Can Matthew come to rescue? Can Matthew help her out? Because we know that the speed at the drop is zero. Exactly, it's zero. Just after a few seconds, it is much, much greater. Then how do we find out the instantaneous speed? We all know about the average speed. It's the total distance upon total time. Maybe we can identify two particular instants, t and t plus h. Respectively, we can calculate the values of distances as s of t and s of t plus h. I can also find out the speed of my duration. That's right, my specified duration, and put down the values in the formula. But right, going back to my problem, what we wanted to find out was the instantaneous speed. Have we reached the instantaneous speed? Well, Mathy is going to find out. What she says is that when the blue dots, they coincide, my h becomes zero. H becomes really, really small, and that is when the derivatives are born, when t and t plus h begin to coincide. So that speed of the duration actually gives me the speed of the instant. My God, that's quite an achievement. Just substituting the values in the formula, and I'm just going to use my formula t plus h whole square, and we can very easily sort it out. H gets cancelled out, minus ct square gets cancelled out on both the sides. And what am I left with? 2 times ct. So my s of I goes into the derivative machine. What comes out is v of I. That's my instantaneous velocity is directly varying with time. So can you think about the graph? What will the graph of a uniformly accelerated motion look like when my velocity is varying with time? All right, another question which I have for you is, what if I send my instantaneous velocity into the derivative machine? What comes out is my instantaneous acceleration. Very interesting to note. Well, it's not at all difficult. We can apply the principles of derivatives that we have learned. We will call it as v of t plus h. Perfectly right. And then it is going to vary with v of t the same way we did for the distance. We can do it for the velocity. That's when my velocity is going inside my time machine, which is my derivative machine as of now. And obviously there is one instant t plus h minus h. So when I sort it out, I'm going to get a small h, perfectly fine. Putting down the values again, you have 2ct plus h minus 2ct. So what am I left with is 2c. That is something interesting to note, that my acceleration, that's my instantaneous acceleration, is independent of time. That's what we call as a uniformly accelerated motion. So we'll stop here for this time. And that's a mild introduction to derivatives and how it is being used in physics. Thank you. Thank you so much, children. That's it for today.